Is I'm gonna, for the final, I'm gonna post all the videos. So if you want to refer back to the lecture, you're gonna have the opportunity to watch the videos and prepare for the final. So that.
The lecture with notes that you haven't posted as well?
Yes.
Okay.
So you're gonna have all the notes, all the videos, so everything you need to do well on the final. Okay? So this is the topic that we started covering on Thursday, and it's the transportation model and the assignment problem. And basically we went through most of the material. We discussed this problem in where we had 3 plants that were supplying energy to 4 cities, and you needed to find the best way to distribute this energy for these cities by minimizing the cost of producing and sending that energy to each of the cities. So we talk about the characteristics of the transportation problem and the transportation tableau, and also we discuss the formulation. Did the same thing for this problem, and I also show you that the transportation problem can be represented as a network. In this particular problem, let me go back a little bit. We were looking at the MG Auto that has 3 plants in Los Angeles, Detroit, and New Orleans, and their capacities of the plants were 1,000, 1,500, and 1,200 cars. And you had 2 demands at 2 different distribution centers for the same period. There were 2,300 and 1,400 cars. And you had 2 different tables that presented the information that you need in order to decide how to send these cars to the distribution centers. One of them is the mileage, and the second table presented the cost. And also, we basically discussed that the cost is related to the amount or the number of miles that you need to travel in order to distribute these cars. So for those cities that you needed to travel more, like this one from Los Angeles to Miami, you'll notice that the cost was high. And for those cities that the distance were short, for example, from New Orleans to Miami, the cost was really low. The formulation is here. We were minimizing the cost of sending those cars from one plant to one distribution center. So this means that you go from the first plant to the first distribution center, and so on. So each distance is represented by the cost to travel that particular distance, and the decision variable is basically saying how many units you're going to send from this plant to this distribution center. And we had one group of constraints for the basically the supplier, and one group of constraints for the distribution centers. The supply for the first plant is Los Angeles, it was 1,000, and the supply for the second plant was Detroit, was 1,500. And New Orleans has a demand of 1,200, Denver had a demand of 2,300, and Miami had a demand of 1,400. So we discussed how to formulate these equations, these constraints, and I asked you to solve this problem using Excel or a bonus for the second exam. And I also asked you to upload that solution to Tracks by Friday. And I checked this morning, and there were no one interested in getting that extra bonus point. Yeah, so that's what I thought, and I didn't send a message. You forgot, so I'll give you until this afternoon, 5 p.m. to complete this solution, okay? So this is the last call. So if you complete that, I'll give you that extra point. Okay, so the general description of the transportation problem, set of n supply points from which a good is shipped. So supply point I can supply the most limited quantity of units. Same thing applies for the demand. So the demand is going to be requesting a number of units, and each unit produced at the supply point and shipped to the demand point incurs on a variable cost. So that's basically the main characteristics of the transportation problem. You have some supply nodes, you have some demand nodes, and you want to send your supply to the demand nodes by minimizing your cost. So as I mentioned on Thursday, this is the main, or this is the general format of the transportation problem. So any problem that you can formulate using the transportation model will have this type of constraint, this type of objective function, and these two types of constraints. Okay, so you know, if I ask you to formulate a problem or formulate a transportation problem, you will have to follow this scheme. So your problem should look similar to this one. Okay? The only thing that you're going to be modifying are the cost and the number of constraints that you will have depending on your supply and also depending on your demand. And I think this was the last thing we did on Thursday. I showed you that by understanding these type of problems, solution methods for these problems, these are always good tools to have for companies that looks at logistics most of the time, such as H-E-B, Walmart, UPS, Amazon. They are always looking for people to improve their logistics and their distribution centers. Okay, so this is new material for today, the balanced transportation problem. And one of the questions on Thursday was, what will happen if the problem is not balanced? Or basically, if you have more demand than the supply, or the more supply than the demand? And that was a good question. So the problems that we have discussed so far are looking at the balanced type of problem in which you have a supply that is equal to the demand. So if total supply equals total demand, the problem is said to be a balanced transportation problem, in which your summation of the supply equals the summation of the demand. So if you produce 100 units of cars and your demand is 100 units of cars, then you know that your problem is balanced, because you're going to be only producing the number of units that you need. But that's not always the case. Sometimes your demand is higher than your supply, and you need to understand how to solve problems for such a case. So balancing a transportation problem is if total supply exceeds the total demand. If the total supply exceeds the total demand, we can balance the problem by adding a dummy demand point. So basically, we're going to create this demand point that is not real, but will help us to solve the problem. So since shipments to the dummy demand point are not real, they are assigned a cost of 0. So shipments to the dummy demand point are not real, then there will be no cost incurred for sending unit to that demand point. Okay, now, balancing a transportation problem is the total supply is less than the total demand. That means that you are producing more than what you need. If the total supply that is strictly less than the total demand, the problem has no feasible solution. So if total supply is strictly less, that means that your demand is higher than your supply. So in such a case, the problem will have no feasible solution because you will not be able to satisfy the demand with the supply that you have. So because one or more of the demand will be left unmet. So generally, in such situations, a penalty cost is often associated with the unmet demand. So you're going to have this cost. Basically, your client is going to charge you if you're not able to satisfy the demand that you promised. And the total penalty cost is decided to be minimum. So you want to send or satisfy the demand of those customers that will charge you less for this penalty cost. Okay, so that's in the case in which you have a penalty for not satisfying the demand requested. So let's use the same example in the MD model. Suppose that the Detroit plant capacity is 1,300 cars instead of 1,500 cars. So that means that now you have less demand. So we're gonna change the demand at this point, and now is 1,200. The total supply now is 35. I'm sorry, this should be 1,300. So the total demand, if you add these through 3 demand or supply points, this add to 3,500. And if you add the total demand, you know that this is going to be higher because total now at this point is the same, is 3,700. So with the current supply that you have, you will not be able to satisfy the demand at these 2 distribution centers. Meaning that part of the demand at Denver and Miami will not be satisfied. So one of these 2 will have a demand unmet. Okay, so again, if total supply equals the total demand, the problem is said to be a balanced transportation problem. But in this case, that is not the case. So because the demand exceeds the supply, a dummy source or plant with a capacity of 200 cars is added to balance the transportation model. So we're going to add this dummy supply node to balance the transportation problem. The unit transportation cost from dummy plant to the 2 destination is 0 because the plant does not exist. But the problem will give you a solution that will take into account this plant that does not exist. And for instance, this could be a solution to the problem. So again, we have our 4 supply nodes, and our 4th supply node now is the dummy plant. So originally we had 3, now we have 4, and we have our 2 customers or distribution centers, Denver and Miami. This number at the top represents the cost of sending a unit from one supply node to a demand node. So the cost to send from Los Angeles to Denver is $80, for instance. And from Detroit to Denver is $100. Now, if you look at these numbers at the bottom, those are the number of units that you're going to see shipped based on your solution. So the solution is saying you have a total supply of 1,000 from Los Angeles to any of these two cities. So the solution is telling you that you're going to use that 1,000 and you're going to send all your units to Denver. Same thing here from Detroit to Denver is 1,300 that you have available and you're sending all of them to Denver. The plant in New Orleans is sending all its capacity to Miami. And finally, you see this number 200 here for the dummy plant. That means that these 200 is the demand that you are not able to satisfy. So what the solution is telling you is Miami is going to be short by 200 units. Now, if you look at the solution, you notice that from table, the units are sent on those boxes where the cost is small. So for instance, from Los Angeles to Denver, the cost is 80, Detroit 100, and New Orleans is 68. For those costs or for those links where the cost was higher, there's no units assigned. Same thing applies to this node. Since the cost is 0, then it's cheaper for you to have those 200 units not satisfied in Miami. Now, the solution shows that the dummy plant ships 200 cars to Miami, which means that Miami will be 200 cars short. Based on this problem and the explanation, can you modify the model to make sure that a specific destination does not experience a shortage? Like, for instance, if you don't want Miami to have 200 units short, what would you do to the problem? And this is related to what I mentioned about the penalty cost. So right now, there's no penalty cost. This is basically telling you 0 is your penalty cost. So if you want to make, for instance, this link, if you want to make Miami, or if you don't want Miami to have 200 units short, you can increase this cost from 0 to, let's say, $300. Now, this cost is going to be higher than all the costs in the problem, which means that if you have 200 units assigned to that dummy plant, you have that penalty cost, your cost in your formulation. I don't think we have the formulation notes here. But if you remember, you were trying to minimize the cost of sending units from one side to the other. If you have this penalty cost to be 300 and you send 200 units, you know that your cost is going to be very high. So what the problem solution is going to do is it's going to take these 200 and it's going to assign it somewhere else. Maybe it's going to move it here and plant up part of the supply that is assigned to Denver is going to be moved to Miami because it's going to be cheaper for you to not satisfy this demand where the cost is 0 than not satisfying this one where the cost is 300. Does that make sense? And this is why I wanted you to solve the problem using Excel, because if you have your spreadsheet, we can modify these costs and see what happened. Okay? So I'll give you another chance to complete that, and we can go back to that on Thursday, and I can show you with the table how the solution is going to change. Or you can do it, or you can try it yourself. If you balance the demand and you have that additional node, if you change the cost, you'll see that the solution is going to be changing because you want to minimize your cost. So the strategy you're going to find out, or the solution that you're going to get from your problem, is the one that minimizes your cost. And obviously, if you have a penalty cost that is higher than the other cost, that will avoid, or the solution is going to avoid this link, and it's going to try to use part of the solution or the supply from this node to satisfy this demand, and maybe move part of the unmet demand to this Denver link. Any questions? Okay, so the answer for this question again, if you want to avoid having 200 units of unmet demand for Miami, you can increase this cost, which right now is 0, to a large number. That will tell the model that now you have a penalty cost. And if you want to avoid that penalty cost, then you need to satisfy the total demand, which is 1,400 for Miami. If you don't satisfy that demand, you know that every unit that you are not able to supply to Miami is going to be penalized with this cost. If you supply all the demand to Miami, then you will not have these penalty costs. Okay? So that's for the case in which you have a larger demand than the supply. Okay, so that basically concludes our discussion for the transportation problem and model. Now we're going to transition to the assignment model, which is a modification of the transportation problem. And you will see what's the main difference. It's a very small difference between the two. So the classical assignment model deals with matching workers with different skills to jobs. So this problem is very used, for example, if you are doing scheduling. The assignment problem will help you assign those workers to a specific task. The goal is to determine the minimum cost assignment of workers to jobs. Okay? So the assignment problem these two problems are very well known in industry and in research. So when you go outside and you're working, let's say, for a OR team, operation research team, this is, I would say, most of the well-known problems are the transportation problem, the assignment problem, and because they can vary, and you can use them for a lot of applications. So basically, the general description of the assignment problem, the general assignment model has n workers and n jobs, and the element Cij represents the cost of assigning a worker I to job I. So you have a set of workers, let's say you have 10 workers and 10 jobs, 10 different jobs. Then you want to find the best way to send or to use these workers to complete a specific job. For instance, let's say this is a doctor and this is a nurse, and you have 10 jobs, say different type of patients. You know that cost of assigning doctor to this patient is 100, but if you assign a nurse, that will cost you 10. Then instead of assigning a doctor to that patient, you will basically assign a nurse because it's going to cost you less. That's that's the type of problem that you want to solve. Or you want to basically save this resource that is more expensive to serve those cases in which you cannot assign a nurse, for instance. Okay, so you don't want to occupy your doctor if you know that you can use it for a more severe or treatment for a particular patient. Okay, so you're trying to assign your resources to a specific task. So the assignment model is a special case of the transportation model. Workers represent sources and jobs represent destinations. The supply, demand, amount of each source or destination exactly equals 1. So you can only assign one of your resources to one of your jobs. The cost of transporting worker to job is CRJ, which is a cost that is going to depend on the particular task that you want to assign, and the level or the skills of these resources. The assignment model can be solved directly as a regular LP. So you can basically use the simplex method. If you have only two variables, you can use the graphical method, or you can use your Excel solver to find a solution easily for this problem. Okay, so this basically concludes the discussion on the transportation and the assignment model. Any questions about this topic? The type of problem that you will expect from this material are mostly related to formulation. So you will have to formulate these problems. I want to see that you can understand how to formulate a transportation problem and an assignment problem. But again, all these problems will follow the same structure. So if you follow the general structure for the transportation problem, it's basically filling out the blanks. So you know that you're going to have a objective function that will minimize your cost. You're going to have a set of constraints for your demand and a set of constraints for your supply, and also your non-negativity variables. So those are the constraints that you're going to have for these two types of problems. So if you follow again, this structure, then your formulation should be very easy to do. Just follow this format. You should end up having a formulation similar to this one. Okay? So I'm going to post that homework today, and then let me know if you struggle or have any problems. So the next topic for today this should be my mistake, but it's the introduction to integer programming. And essentially what you're going to see today is a different type of model for your problems in linear programming. And this is coming from chapter 9 from your textbook. It's integer linear programming. And you will see that the difference of how to formulate an integer programming model is very small. So if you know how to formulate a linear programming model, the major difference is going to be based only on the decision variables. And also, the other difference that you will notice is how to solve these problems. So now the simplex algorithm doesn't work anymore. And you will see why. So I think I discussed briefly what an integer programming was at the beginning of the semester. We're going to go a little bit more in depth about these type of models and why are they so useful. So again, as always, I'm listing the course objectives. So basically up to today, we have covered most of them or all of them. Now we are gonna go back to formulation, and this will apply to multiple course objectives such as developing linear programming models, solve the models, and interpret the model solutions. So we're going to go back and apply these course objectives to the new material for today. So the learning objectives is learn how to formulate an integer programming model and discuss how to solve integer programming models. And the two readings sections that you can use from your textbook are these two. It's very short sections. Illustrate the applications for integer programming and the branch and bound method or algorithm, which is the solution method that we're going to discuss in class for solving integer programming model. So the agenda, I'm going to provide an introduction with an example. Then I'm going to explain three major types for integer programming models. Then also I'm going to discuss some examples that are related to the integer programming types. And finally, we're going to go over the solution methods. So the solution method is material for next time. So in introduction, basically, integer programming or IP is a mathematical optimization program in which some or all the variables are restricted to be integers. Okay? So, as an example, I'm going to use this problem that is coming from the airline industry, which is you want to decide how many units you want to add to your current number of airplanes. So this airline is a small regional company that specializes in flights in small airplanes. So the companies are starting to do well and decided to expand their operations. So the basic issues facing the management is where to purchase more small airplanes, to add more small or short flights, or to add a larger or more larger airplanes to start moving into the national market. So you want to decide how many units you want to add from both types to your current company. So the question is, how many airplanes of each type should be purchased to maximize their total net annual profit? Okay, so the problem is you have two types of airplanes and you want to know how many of each type you want to buy. So money that you have available is 100 million, and you have some information in terms of the net annual profit per airplane. So for a small airplane, you make $1 million per year, and for a large airplane, you can make about $5 million. But you also have to consider the cost of buying each airplane. So small airplane can cost you $5 million, and a large airplane can cost you $50 million. And you have also a constraint in terms of the number of airplanes that you can buy for the small size airplane. So you can buy at most 2, but you don't have any limitation in terms of how many large airplanes you can buy. But if you look at your cost and your money, the money that you have available, you know that at most you can buy 2 large airplanes. It's not strictly stated, but based on the cost and the money that you have available, that's the best you can do if you decide to go for large airplanes. Now, the linear programming formulation going to have two decision variables, S and L. This is the first time you see a different or this notation for a decision variable. Again, for a decision variable, you can use any letter. I decided to use S and L for this problem just to make distinction between small airplanes and large airplanes. So S is the number of small airplanes to purchase, number of large airplanes to purchase is L. And you want to maximize your profit, so you know how many millions you're going to make by having each type of airplane per year. So for the small airplanes, you're going to make 1 million. For large airplanes, you're going to make 5. So you want to maximize that profit, but you have some capital available, which is 100 millions, and you know how many each airplane is going to cost you. So 5 million the small airplanes, 50 million the large airplanes. So depending on the number of each you're going to buy, you know that the most that you can spend is 100 million. And you also have another constraint, which is basically that you cannot buy more than 2 airplanes for the small airplanes. And in terms of your decision variables, you are making them greater or equal to 0. Okay, so that's our model. Since we only have 2 decision variables, S and L, we can solve this problem using the graphical method. So we have one constraint, which is this one, S less than or equal to 2. So that's our first constraint. Then we have another constraint for the second, which is the money that you're going to spend. And finally, we can define our feasible medium. So we know that our solution is going to be here at some point. As we know, when you use the graphical method, you need to show where the solution. So you have to basically draw the plane and wait until the last one that you're going to touch with that plane. In this case, the optimal solution is this point here, and you see that the optimal solution is 2 and 1.8. Do you see any problem with that solution? Okay. Correct. So 1.8 is not an integer solution. So you're basically saying you're going to buy 2 small airplanes and 1.8 large airplanes. That doesn't make sense. Okay? So the methods that we already learned in class are not working when you have a problem that has integer variables, in which you have to say the solution has to be integer values. So this solution is optimal, but it's not optimal for the integer programming type of models. So we have to touch on the divisibility assumption of linear programming. So decision variables in linear programming models are allowed to have any values, including fractional values that satisfy the functional and non-negativity constraints. Variables are not restricted to just integer values, and that's in linear programming. Since the number of airplanes purchased by TBA must have an integer value, the divisibility assumption is violated. So that doesn't apply to our models anymore. Okay, so solutions that are fractions are not optimal for integer programming. So what do we do now? Can I go to the next slide? So the formulation stays the same. This is the same formulation that you have on the previous slide. But now, if you look at the decision variables, S and L are integers. So in your formulation now, you need to state that your decision variables need to be integers. You can use the graphical method if you have two decision variables, and these are the steps for the graphical method. But the main difference now with the graphical method is that you're going to stop at the last instant where the straight edge passes through an integer point that lies within this feasible region. So instead of going to until the last point in the feasible region, you're going to stop at the last integer point that crosses that line. This integer point is the optimal solution. And I'm going to show you again using the same problem. Now I'm highlighting those points where you have integer solutions. So if you draw your feasible region and you look at the plane now, your optimal solution, the last point that touched the feasible region in which you have your decision variables as integer, is this point. It's no longer this point. This is the optimal solution for the linear program. But for integer solutions, in this particular case, this is the last point in which you touch a solution where both of your decision variables are integers. So the optimal solution for our problem is buying 0 small airplanes and 2 large airplanes. That will give you a profit of 10 million per year. Okay, so why do we need to solve integer programs? The advantages of restricting variables to take integer on integer values make the problems more realistic, and also will provide you with solutions that you can really apply. The disadvantages of restricting variables to take on integer values are that they're difficult to model and difficult to solve. And I'll show you why they're difficult later in this lecture. But the idea is represented here in this figure. So when you look at the integer programming model, your feasible region is constrained by this area that is represented by the light gray. And you can use the simplex method to go from point to point without problem, because you know that your solution in the linear program is always going to be in one of those endpoints. But when you look at the integer programming model, your feasible region is now constrained within the linear program model, because your feasibility region is now more smaller than the other one, because you're constraining your feasible region to integer points. You know that if you pick any solution outside this area, the values that you're going to get or obtain are fractional values. And they are not going to work for your solution if you have a integer variable. So always you can think about having your integer feasibility region is going to be always smaller than the one for the linear program, because you are making that feasible region more constrained by adding the constraints of having your decision variable to be integer. And in order to go from here to here to find a solution, we need to discuss some methods, but it's very hard and very difficult. Okay, so we're going to have multiple or different types of integer programming models. The first type of model is the one that we call pure integer programming problems, and are those where all the decision variables must be integer, such as the one that we just discussed, all the decision variables are integer. You can also have a mixed integer programming problem, which only requires some of the decision variables to be integer. So you can have some of the decision variables to be continuous, such as the one that we saw on linear program, where they can assume fractional values, but you can have a group of the variables that needs to assume a integer value. And you also have binary integer programming problems. It are those where all the decision variables restricted to integer values are further restricted to be binary variables. So binary variables means that the solution can be either 0 or 1. So you can see these type of problems if you are solving to locate a facility on a particular, let's say you want to allocate new facility for Walmart somewhere in Texas and you have multiple locations. You want to have a decision variable that is 1 for the area that you select and 0 for the other ones. Such cases, you will have binary variables because your solution is either you select that location or not. If you select that location, then your decision variable will be equal to 1. If not, then the decision variable would be 0. So, model integer programming, mixed integer programming, and binary integer programs. Difference are highlighted here. Integer programs, all of the variables are integer. Mixed integer, some but not all are integer. In binary integer programs, all are either 0 or 1. Now, the LP obtained by omitting uninteger or 0-1 constraint on variables is called the LP relaxation of the integer program. So if you go backwards, you know, I started the lecture showing you the solution for the linear program, and then I show you the solution for the integer program. If you go backwards, you start with the solution of the integer program, and then you find the solution of the linear program. That's what we call relaxing the integer program, because you are not constraining your decision variables to be integers. You are making them linear programs or linear variables. And sometimes this is very useful if you're not able to find a solution for the integer program. You can relax that constraint, find a solution which is continuous, and use your judgment to make a decision based on the fractional values that you can get. But that is not always recommended. Okay? But that could be something that you can do. Okay, so let's discuss some of the linear program models that are useful. So for instance, if you're working for a company, you might be encountered with situations in which you need to allocate some of the money of the company. So capital budgeting allocation problems. For this example, we have 6 different types of investments. So here listed from 1 to 6. We have the cash required. So in order to buy each investment, you need to make an investment in terms of money. So first one costs 5 million or 5,000, second one 7,000, and so on. But you have net present value for each one of the investments. So for instance, this one is the one that pays you more at the end of the period, which is $22,000. So based on this information, the money that you have to invest and the net present value after a period of time, you want to find the best way to allocate your investments or your money. The cash available for the investment is $14,000, and you want to maximize your net present value. So what will be the optimal strategy? That's the question. An investment can be selected or not, or one cannot select a fraction of an investment. So this is basically making you aware that you either buy the investment or not. Okay? So it's not that you can buy 50% of the investment or 75% of the investment. If you're going to buy the investment, you have to buy it completely. So that is basically forcing you to use integer variables. Okay? So let's look at the formulation. So what will be your decision matter? And basically that relates to, say that again? Not necessarily. You know that you have to buy the complete investment or the whole investment if you go for it. Correct. So your decision has to be whether you buy or not one of these investments. Okay? So XI, this could be 1, 2, 3, up to 6 because we have 6 investments. Is 1 if we invest in project I, or 0 if you don't. Okay, so if we have X1 equals 1, X2 equals 0, X6 equals 1, so that means that you are investing in project 1 and project 6. And you are not investing on 2, 3, 4, and 5. That could be a solution. Okay, so the next part is the objective function. So again, you want to maximize your profit, and you know the net present value for each one of the investments. So investment 1 will give you 16,000. Investment number 2 is going to give you 22,000, and so on. So at the end, you want to maximize your net present value. Now let's look at the constraints. So you have the most, or the money that you have available for your investment is 14,000, right? So that's your capacity. And now you also know the amount of money that you can invest, or that you need to invest for each type of investment. So for the first one, you need to make $5,000. For the second one, 7. For the third one, 4. And you know that if you select one of them, the most that you can spend on those investments is $14,000. So you know that for each decision variable, you will have only a value of 0 or 1. So if you, so if we have the following, would that be a feasible solution? This one? Why not? Correct. So if you have x1 equals 1, x2 equals 1, and x6 equals 1, if you substitute those values here, that means that this is 5 plus 7, that's 12, plus 6, that's 18. That will not satisfy this constraint. You're going to go over the money that you need to invest. So I'm not gonna give you that also as an assignment. If you can find that You don't have to submit that, but try to find out the solution for this problem using any of the methods he had. For this problem, you can also try enumeration, like try to substitute the values 1 or 0 and see which one gives you the highest objective function, or you can solve it easy the solver. But I will discuss the solution next time. In essence, what I want you to see is, at this point of the semester, what I want you to see is that there are some problems that are already studied that are general, that you can reference them every time you have a situation, a real situation. This is one of these problems. As you can see, this problem only have the objective function and only have a constraint. Only one constraint, single constraint. This problem is called a knapsack problem, and I'll discuss on the next slide. But what you can see is the general characteristic of the problem is that you have capacity, and you need to allocate that capacity somehow. So you will only have one constraint and one objective function. So the capital budgeting allocation problem. What is the problem with the characteristics of the previous problem called the knapsack problem? It is an abstraction considering the simple problem. You think about this example, a hiker trying to fill her knapsack to a maximum total value. Each item she considers taking with her has a certain value and a certain weight, and an overall weight limitation gives the single constraint. So every time you have a problem that has the characteristics of this type of situation in which you're trying to fill the bag, where you have some constraints in terms of capacity limitations, weight limitations, and so on, that can be modeled using the knapsack problem. So again, you're going to have only one constraint and one objective function. Practical applications, project selection and capital budgeting allocation problems. Storing a warehouse to maximum value given the indivisibility of goods and space limitation. So again, transportation assignment and knapsack problems, very well studied, very useful in general. Now, second example, this is called the fixed charge problem. In this example, we have a cloth company that manufactures 3 types of clothing: shirts, shorts, and pants. And for each type of shorts or of each type of clothes, you have a requirement in terms of labor and in terms of materials. So, for example, the shirt requires 3 hours of labor and 4 yards or square yards of material. Same thing for shorts and pants. And you also have some revenue and cost information. So, for example, sales price for the shirt and the variable cost for producing that particular shirt. So, you need to take into account, this is more like a manufacturing type of problem or production type of problem, the cost that you will have to incur for producing this clothes, and also the materials that you're going to be using, and the labor hours that you're going to be using. So we have 3 different type of constraints here. We have the labors, hours, we have the material type of constraint, and we have the cost to consider, and the revenue to consider. So the problem is also giving you more information in terms of the machinery needed to manufacture each type of clothing must be rented at the following rates. So you don't have this equipment in your facility. You need to rent this equipment based on your demand. So if you rent a shirt machinery, that will cost you $200 per week. A shirt machinery, $150 per week, and pants machinery, $100 per week. Each week you have 150 hours of labor and 160 square yards of clothes. So right here you have your capacity limitation in terms of hours of your resources, and you have your limitation in terms of your materials. So let's use this information, try to formulate this problem. So what will be your objective function? Well, first, what will be your decision matter? So this is a production problem. You want to know how many units you want to produce for each type of cloth, right? So you want to know if you want to produce 50 shirts, 20 shirts, and 100 pants. So that's your decision. How many of each unit you're going to produce? So what will be the optimal strategy? How many of each type you're going to produce per week? So your decision variables: number of shirts produced per week, number of shirts produced per week, and number of pants produced per week. You need also to consider a second group of decision variables, and you will see why this is useful. You need somehow to tie your production to whether or not you're going to need to rent a specific machine. So if you need to rent a specific machine, let's say you end up producing shirts and pants, then you would not need to rent a machine for the shirts, for instance. So these decision variables are going to tie whether you're going to produce this type or not, to tell your facility manager that you need to rent a particular machine or not. So two groups of decision variables: the production and the ones that are going to decide whether you need to rent or not a particular group of machines. So what this is going to do is, if you decide to produce pants, then this decision variable has to be 1. Because if you decide to produce pants, you know that you're going to need one machine to produce those pants. So if xij or xj is greater than 0, then this variable has to be 1. Or needs to be forced to be 1, because you're going to need that machine to produce those units. Okay, so the objective function, you want to maximize your weekly profit, and your weekly profit is based on this. So you have some profit, your revenue for each type of cloth. Then you have cost for producing those clothes, and you also have the cost for renting the machines. So you want to maximize your total profit. You're going to have a constraint for your labor, so you know that you have 150 hours and 160 for your materials. And this is your optimal solution. Is that solution correct? Any comments about that solution? So this is saying that you're going to produce 30 type 1, I believe this was shorts, and then 10 for pants. Go back here. So you have shirts and pants. $30 and $10. So those are integer values. That is correct. So there's no problem with the integer values. But this is saying that y1, y2, and y3 is 0. Does that make sense? Why not? Right. So you're saying that you're going to be producing 30 and 10, but you don't have any machines to produce those. So again, this decision variable is saying if you produce shirts, then you need to have this decision variable to be 1, because that is what's going to tie your cost of renting that machine. So what do? So if you produce 30 units, you know that Y1 is to be equal to 1 in order to have the equipment available to produce those units. So one way to solve this problem is having these constraints. What this is saying is, again, M represents a large number. So if you decide, or the problem gives you a solution that decides to produce 10 units of the first type of clothes, so let's say x1 equals 10, then what happened to the right hand side of that constraint? And this is 100. M1 equals 100. This could be any number. Let's put 1,000. N is a large number. What this is going to do is it's going to make y1, because if y1 equals 0, this is 0. But if y1 equals 1, then this side becomes equal to 1,000. So now 10 is going to be less than or equal to 1,000. And that constraint is satisfied. So what that constraint is doing is forcing y1 to assume a value of 1. And that will make the objective function consider the cost for having that machine or for renting that machine. So at the end, now the optimal solution for the problem is different, because now you're considering the cost of renting machine 1. So the optimal solution is 25 units, and you're renting 1. I think I'm gonna stop here. We have another problem to discuss. Yes, I have one more problem to discuss, but we're gonna leave that one for next time. Next time, I'm gonna discuss the solution for the solver, and also complete this lecture. And we're probably going to have a lab that I'm going to consider. If you solve it and you do it right, I'll probably give you extra points for the next exam, so to help you improve your grade. So again, this is all for today. And if you have questions about the lecture, homework is going to be posted this afternoon. Or if you have questions about the previous exam, just let me know and we can talk about it. Okay, so I'll see you on Thursday.